involved in projects titled Pilot Scale Development of Biomass Co-firing with Pulverized Coal and a pilot scale setup and study on oxy-fuel combustion for Indian coals. These projects are carried out under the MOU with Fredstep and are funded by the European Union. In addition, he is also working on development of chemical looping combustion technology for high ash Indian coals. I kindly request you, Dr. Manna, to deliver the session.
Handling the session up front is the most difficult one I do my best to keep it engaged. Here is my topic of the talk. I'd like to touch upon the CO2 emissions and consequences and introduction to the biomass and the behavioral experience of biomass. I also like to give on the oxy-fuel combustion and introduction and behavioral plans about the oxy-fuel. As you are aware that we are currently involved in executing two projects and the biomass co-firing with coal, which is already completed, and biological testing of oxy-fuel combustion, which is in process. Coming few months, we're going to fire the oxy-fuel combustion with high ash Indian coals with a different recycle rate. You know, seeing it, but I just touch upon. We all know that CO2 is one of the elements that contributes the maximum to the global rising temperature. If you look at the statistics, you could see that 82% of the total global warming is coming from CO2. So CO2 is no bad element. But I would like to keep you a fact. Without CO2, if there was no CO2, then our global average temperature would be much lower, as much as 22 degrees Celsius lower, which is not comfortable to the many of the human beings and other animals. So the sustaining of the earth would be much more difficult. But how come they are good element, they are bad? No. Let's look at the statistics. So that's where the statistics very useful. If you look at it, 1890 plus less than 2 gigaton, and until 1950 it's not crossing 4 gigaton, but suddenly in 2012, of course in a span of 30 to 40 years, it's 32 gigaton. So that's the quantum of CO2 that is being exerted into the atmosphere from day to day. That's why it is now time we are taking it back, its consequences. So as a result of that, the CO2 ppm earlier was much less than 280 ppm, now it is 400, I think it's already touched 400, and it's going to rise up to 470 or 500. As a consequence, as we know, it may rise between 2 to 6 degrees Celsius by the end of the century. So we are now speaking about per capita CO2 emissions and energy consumption, but unfortunately, it's not so when it comes to the consequences. You could see the African Asian countries are most vulnerable for the rise in global warming and consequently the sea level rise. So it's everybody's responsibility to tackle the CO2. So now we understood that CO2 is one of the main reasons for this. So where are we getting the CO2 into the atmosphere? Then we look into the again statistics. You could see the electricity and industry is contributing close to 61%. And the transportation is around 23%, which is very difficult to capture because it's a scattered source. Whereas industrial electricity is a concentric source. You can capture at one point in a large quantities of CO2. So that's why there was a lot of focus on power plants and industries. We always have about why power plants and industries. That's the reason, concentric sources. So these are the technologies that we have seen, and I would like to just go into the India's power scenario. These are the CEA data as of June 2013. You could see that thermal energy is contributing only 68% of the total energy that is being used in generated in India. This is on par with the global energy levels. If you compare the global energy levels, this is on par. But if you look into the specific thermal energy, then out of all, 86% is coming from coal. And we are going to double our capacity in coming few years. That means that we are going to emit a lot of CO2 from coal. So that's the one thing that we have to concentrate from number. But actually, I got this information from the Waste and Energy International 2013 August edition that there are the potential renewable energy generation in India, and out of which we are utilizing approximately 1/3 of it. So what I would like to mention at this point is we have a lot of potential, huge potential, but out of which only 1/3. If you look at the biogas and biomass, it's close to 21,000 megawatt, but what we achieved was 4,000, 1/5 of it. So there is a lot of scope for us to explore in biomass and biogas generation. So now, till now I talked about the CO2 emissions and the consequences and all. Now if we look at the technologies that are available, all of it we have seen in these presentations. And the one which is I'm going to talk a little bit elaborate is biomass combined with coal and GHMH2 gas. And then first we start with what, why, and where about the biomass. Biomass is a renewable, carbon neutral fuel. Renewable because we can generate endlessly, and it's a carbon neutral fuel because whatever CO2 that's emitted into the atmosphere by biomass can become again a fuel, and that process goes on endlessly. Whereas in case of coal, whatever CO2 that is emitted into the atmosphere, it remains as CO2. I mean, it cannot convert to a fuel again. Whereas in case of biomass, it can become a fuel. On a short rotation crops, we dedicated biomass plantation. By doing so, we can regenerate these fuels and then use it continuously. So, being agriculture, one of the largest food producers, India has a lot of agricultural waste, such as rice straw, wheat straw, and coconut shells, and rice husk, palm trees. There are so many biomass are available in India. And again, one more fact I would like to keep in front of you, that if you leave the biomass in the atmosphere, by anaerobic process, most of the carbon converted to the methane, that is much more dangerous global warming gas than CO2. So this is another point we have to keep in mind and look forward to the renewable uses of renewable fuels in thermal power sector and other plants. And again, it can be as we see yesterday, that we can use in a AC-fired boilers or CFPs and ILCC and anyway. So I would like to give you some rough estimate about the CO2, the biomass capability in India. If you look at the total arable land in India, it was around 392 million acres. All this land is used for some or other agricultural production. So that means that we are bound to get some agricultural waste. So if that is the case, I have presumed here that we are using all the land for the rice production. For every acre of rice production, we will get 2 tons of even more. That's right. 2 tons of rice straw. This means that we are going to get around 784 million tons of rice straw per year, which will contribute to 65% of the current thermal energy that we are producing in our power plants. So there is a huge potential is available. Of course, I don't want to talk about why it's not happening. We all know that it's a very difficult process, but I want to talk here about the capability, the quantum of the biomass that is available, at least on a paper, is huge. So now I would like to go over a little bit overview of the biomass combined systems across the world. And there are many plants that are available which are applying either demonstration scale or a commercial scale or maybe some large scales. There are many plants that are available, and even now some are doing. For example, France, they would like to fire biomass up to 50%. One of the sources I had from. So among all the European countries, if you take, the Finland is the maximum, which is utilizing around 13.7% of their mass for power generation. They were using up to 28% for power and other usages. And again, there are many plants, as I said, and most of the studies that shows that biomass can be fired 15% on energy basis and 20% by mass. And some studies insist that we have to go for a separate burner for co-firing the biomass, easy fire only. So what are the advantages of biomass co-firing with coal? Apart from getting a carbon neutral fuel, and we also have some other advantages, like we can reduce the exposure to emissions. And it depends on the fuel, but most of the biofuels have a lower sulfur content than coal. And again, this can be generated endlessly. Unlike coals, which have a fixed resource, if you keep firing the coal, then after 150 years, I think we won't be having any coal. Then we necessarily have to depend on biomass. So, but biomass can be endless fuel. And the load on ESP can be reduced. This is mostly true for the Indian coals because we have high ash content. The biomass will significantly reduce the ash because it has very low ash. And it has some inherent oxygen, as Professor Klaus has mentioned that these are young fuels. These are very young when you compare to the coal. Because these are younger, it has a lot of oxygen which is available in its fuel itself. So we can reduce the total air supply needed for the complete combustion. So, although there are many advantages, there are also issues. We may need a separate burner, but if you cross the burner, if you fire a very high percentage with coal, it may cross the burner because of its nature. And it may reduce the ash melting point, as we have seen yesterday, Professor Frost was explaining. And because it has some elements like chlorine, which causes high temperature chlorine, and some of the other metals like phosphorus, arsenic, and chlorines, which will spoil the catalyst in case of DeNOx system. So let's compare the behavior of the ash for coal and biomass. And these are all from literature. So I haven't here with the BHEO's experience as of yet. So the coal ash, which is mostly consists of aluminum silicates and minimal quantities of iron, calcium, magnesium, sodium, and also the phosphates and the chlorides and the sulfates. Whereas in case of biomass, these are all in significant quantities. Whereas in case of coal, we can neglect that, but in biomass, they are in significant quantities. That may lead to low temperature evaporation of chlorine, and that may further react with sodium and other alkali materials and produce high temperature chlorine. And also, as well as it will reduce the ash during temperature. So that's another problem that may cause more slagging near the pleasant region. And this is where the entering into the BHEO's test facility that we have at the solid fuel burning test facility. It primarily consists of a coal milling system. This is a mill, and this is an indirect firing system where we pulverize the fuel and then store it in a PCB, and from there we send to a burner. So this is a mill. From there it goes to a cyclone separator and a biomass filter, and the resultant pulverized fuel will be stored in a PCB. From there, and a separated element, we take the air. That air will be preheated to approximately 300 degrees Celsius, and from there it will be split up into two components. One is for the burner, another one is to carry the fuel to the horizontal fire furnace. This is fitted with a wall burner, and again the air which is sent for the burner will be split up into several components to reduce the NOx and other efficient combustion. So, to this system, we have embedded two elements which are important for the biomass. One is the raw biomass lane, and another one is the pulverized biomass lane. So, the dotted line indicates the appended systems to the existing facility. So, this is what, and we also have added a screw conveyor which will carry the biomass into the burner. And we tested in two kinds of once biomass is mixed with the coal, mixed wood pellets, here biomass is wood pellets mostly, the wood pellets were mixed with the coal prior to the mill and then sent to a mill. So that way, I mean, when it is pulverizing, it's a complete mixture of biomass and the wood pellets and the coal at different proportions. We tested around 10%, 20%, 30% by mass and coal. And whereas in other case, like for example, rice husk, which is a very low density, when you send to a mill, it so happens that it will directly head to the classifier. We have a static classifier that may escape to the classifier, which is unmilled. So the size will be significantly higher. That's why we have separately milled and stored it in a peak in a pulverized biomass bay and then sent to a burner. Near the burner, the coal and biomass mix together and then fire. So these are the fuels we have used. These are the coal, and this is a pelletized wood that we bought from some vendor in Western India, and this is a rice husk. These pellets made us much easier for handling, and I'll just give a brief details about the approximate and ultimate analysis of the coal and biomass. Here, for the sake of comparison, I also put the process Juliflora. You can see that the moisture is almost the same with our coal, but when in case of volatiles, significantly higher than that of coal, as much as at least twice higher. And again, ash, you can see from here, it's Indian coal, typical Indian coal is around 38.4%, and wood pellets is less than 2%, and again, Juliflora 5%, but somehow rice husk has more ash. Similarly, you can see that oxygen content is much higher compared to the coal. It is at least twice higher, and sulfur content is lower, and also the nitrogen. So, and one more important point: typical Indian coal has 3,860 kilocalories per kg, but the process of Juliflora and wood pellets have higher calorie value than coal. So it's more beneficial for Indian power plant owners to fry biomass. And some of the analysis that we have done at the lab, computer-controlled scanning electron microscopy, to analyze the different elements prior to the combustion so that we can take some precautionary measurements. So you can see that most of the biomass, I mean these two biomass, rice husk and wood pellets, has very high quats, and again, the aluminum silicates, either potassium, kernels, or calcium, which are higher in coal, whereas in case of rice husk and wood pellets, which are much lower. So that means that the ash figure temperature may be lower, that indicates this point. And again, the chlorides, we didn't touch much in some parts of the coal. So, and it was also true from the literature that if you fire wood pellets, there's no problem. You can straight away go ahead. And this is the test facility that we have at our village here. And this is a burner, and this is a horizontal furnace and chimney. And the air and the coal are put in different ports into the burner, and that will fire that furnace. These are the few ports that we measure heat temperature profiles are maybe visual observation and maybe heat flux sensor that we have. And this is a firing picture from the side view of the burner. And this is 100% coal, and this is wood pellets with coal at 1:4 proportion. I mean, 20% is wood pellets and 80% is Singareni coal. And you could see, and from the rear end, and you could also see that. And we have added a few more elements into the furnace. These are the cooling tubes, just to collect the deposited ash and further analysis in the lab. And some of this is here in picture. And most of the coals looks spherical in nature, whereas in case of biomass, it's flaky in nature. So that may cause some problems in globally. That we have observed, I just discussed now. And some of the people have a perception that when you use a biomass, it may not be polarized to the fine level as much as close to coal, but it's not true. Of course, these observations were limited to wood pellets. You can see when you fire D50, if you see 74 micron per coal, whereas in case of wood pellet, it is 62 micron. But surprisingly, on D90, it is 250 per coal and 350 per biomass. When we see closely, that is because of the 4.5% between 500 to 100 micrometers. That's because, as I said earlier, the biomass is a flaky kind of nature. That's why the size is much higher. It's not spherical, that's why the size is higher, it seems like. So these are some of the optical biological temperature measurements across the depot. And you can see that for biomass, the orange line is the biomass, and the blue one is the coal. And the coal, the peak temperature is almost the same. I mean, because the calorific value we will get, they are very close for Indian coals and biomasses. So we didn't observe much peak temperature difference. But the occurrence of peak is a little bit different. That's because one of the guests was like, biomass has higher volatiles. So when you suddenly enter into the hot firing zone, it immediately releases the volatiles, which are larger in quantity. That makes the flame to catch much faster. So the flame front can be shifted a little bit close to the burner input. So that's one observation. And you could see the flue gas composition for 100% is coal and 10% and 20% is wood pellets is coal. And the CO is decreasing. This was the supporting our flame, like because of higher volatiles, the flame release stability and flame release much better. With, although it's significantly not very significant, but still it's a better conversion. As well as the NOx is reducing because of the lower fuel nitrogen. And CO2 is almost the same. And these are some of the depositions that we have observed. This is only physical observation. And the similar deposits were observed for when we fired biomass with coal. So these are some of the European Union visits to the BHER test facilities. As a part of the project, they have come here to see the demonstrations. So these are my observations, our observations based on the biomass coal with coal. And we have observed some flowability issue, as I mentioned earlier. And this was more significant when it is when the biomass proportion is more than 20%. So this is because mostly due to our indirect firing system, where we store the polarized fuel and then separate the pilot. That's the reason behind it. That's what we observe. And most of the flame temperatures and heat flux for the biomass and then coal are the same. And this is the one important point that we have observed, particularly for the Indian coals, because the Indian coals are more inert in nature because of high ash content. These biomass have and some of the power plant customers have reported to us that they are facing some flame stability issues for certain coals. In those kind of power plants, if they implement the biomass co-firing with coal, because of higher volatiles, so that will be helpful for them to stabilize the flame and operate it at far loads, maybe 50% or less. And these tests were mostly conducted for not more than 6 to 8 hours. And during the testing, we did not observe any significant falling or slagging or other heavy works. So since we have that, we have got some experience in biomass, wood pellets co-firing with coal. So we are now gearing up for the commercial implementation of biomass co-firing, the wood pellets co-firing in a commercial plant. So we have identified that based on our experience, we don't have to make any modifications in the polarizer for the burner design or the furnace internal components. But we may need a separate biomass bin and maybe conveyor. We could see that picture in here. This is what our plant is. We have a typical coal yard, and from there coal is conveyed to the bunker, from there to the mill, and to the burner, or to the furnace. So we near to the foliar, we can make a small biomass gap with pellets. From those pellets, we can feed into a biomass supplement. From there, we using a volumetric feeder, we can control the amount of biomass that is being fed into the power plant. So we say that on a layer of coal, if you can add another layer of biomass, when it is falling into the bunker, it mixes, better mixing will occur. The same, when it goes into the pulverizing, even better mixing occurs. So more or less we can get a uniform or close to uniform mixing between the biomass and coal, so that we don't have any other issues. And these are some of the estimates from based on wood pellets. For a few of 210 megawatt, we may need around 3,120 tons of fuel per day. When you compare with biomass of 5%, then we may need 156, and we are reduced up to 624 tons per day. But we may benefit in reducing the ESG load. By 5% it is 4.5%, by 20% it is 18%. Reduction in ash on ESG. So that we can overall quantity of ash emitting from the power plant can be reduced by co-firing with coal. And similarly, SO2 will be reduced, and it mostly depends on the sulfur content in the fuel. A minimum of 25. But some of the fuels, like in the morning, Professor Krauss, I was telling that the sea base was having a higher sulfur content as much as 6%. In that case, it's not true, but most of the biomass is true. And our pilots were testing the particle conversion. We have seen this slide, and now I am focusing on this technology. As we are aware from previous lecture, there were different methodologies to capture CO2, pre-combustion, post-combustion, and also combustion, and also chemical decompression that Dr. Abdul was describing, carbon looping and chemical looping combustion. So then how it is in oxyfuel combustion, and here the process changes significantly. In case of air, you have oxygen and nitrogen, and when it completely combusted, then you will get CO2 and H2O and nitrogen, where the nitrogen is as much as 70%, or close to 70%. So it's very difficult to remove CO2 from this mixture, although there are some post-combustion methods available, but still it's more expensive. Whereas in case of biomass, in case of oxyfuel combustion, we can fire coal in presence of oxygen, so that you get the CO2 and H2O as an end product. H2O can be removed by condensing it. You will get more the CO2 that can be sent for direct storage, capture and storage. But however, we may have a higher temperatures in the combustion zone because absence of nitrogen, as much as 3.7 moles of nitrogen, which is absent in oxyfuel combustion, that may lead us to higher temperatures, as much as 2,500 degrees Celsius, even higher. So further, the recycling has been adopted in most of the cases. So where the flue gas will be recycled back to the water, so that the same flame temperatures as that of the air can be maintained. So there are some advantages. Like because of absence of nitrogen will not be reduced significantly, as much as 90% is reported in the literature, but commonly 2/3 can be reduced. And volume of the flue gas also can be reduced. So because of the higher specific heat of the CO2, so the plant size can be reduced, or we can get a higher output. And it facilitates the direct CO2 capture, and it's less expensive than the post-combustion capture. And it can be easily retrofitted into different existing systems. So there are some challenges. Then ASU cost, how to get the oxygen. You need to install ASU that may reduce the efficiency to 10%. And as for the emission, also because we don't know, we don't know in the sense there are reports like SO2 instead of SO2 will get more of SO3, like more corrosive in nature, at the NOx level and how much. And what is the recycle ratio of the flue gas? That one has to do for their own course. Literature says some numbers, but still we can apply 2 types of facilities to the power plants. And CO2 transportation and purity of the CO2 in each power plant streams. And this is the facility as I explained earlier. And the dotted line shows the artificial combustion retrofitting. So we have to add one cyclone suppressor to remove the flue gas and as well as the cooler. This I'm talking with reference to our testing at BHER. And this is a HER fan. And there will be split up into two components. One component will go to the burner and another one will go to the capture and storage, but in our case it is atmosphere. So where it will be split up into several components as discussed. And these are the systems that are needed to be configured for the existing facility. An air separation unit, and a flue gas recirculation system, and CO2 combustion unit, and CO2 transportation system for storage or utilization. And these are some modifications we have done at our facility. We have installed a 400 kilowatt oxy-fuel burner and a cyclone assembly to remove the ash and heat exchanger. A gear fan and flue gas ducting and storage tank. They are all come to very end. We will start these experimentations in a couple of months. And flame stability at different. These are the plans that we wanted to execute at our facility. The flame stability at different flue gas recirculation and air cooling oxy-fuel parameters that we wanted to find out so that we can retrofit the existing facilities and excess oxygen ratio that is needed for the complete combustion in case of oxy-fuel and the emission quantities and different varieties of the flue gas recirculation. We can do it at different levels, wet, dry, or combination. Thank you very much for the BHER and the European Union for giving me the opportunity. Thank you for it. Thank you very much.